necessarily matters.
I think it's okay. I mean, it's just a constant.
Yeah, good point. I agree with you.
I mean, it's dark and.
I'm just, playing devil's advocate.
Anyway. I'd rather have it be nice for the lecture anyway.
I'm just going to the morning battery play a lot of battery.
Okay, so let's start the last talk for today, which is by Professor Li on the standard zero-free region for Rankin-Selberg L-functions on GLN.
Peter helped my career in various ways, and I'd like to thank him on this occasion. So let's start from the classical Poisson's method in deriving. Didn't hear me, but thank you. The classical Poisson's method in 1899, Poisson, so he proved the zero-free region, y minus a constant divided by the log t. So that's so the zeta doesn't vanish on the one line is equivalent to the prime number theorem. But here, with a zero-free region, we can get an error term in the prime number theorem. So his method is to construct a dirichlet series d of s with the following properties. The first condition is it has positive coefficients. Second condition, it has a pole at 1 to order k. The third condition, if the L function vanishes at sigma plus it, and d of s vanishes at sigma to order strictly bigger than k, then the L function, L of s, has a zero-free region like the Riemann function. So if d of s vanishes at a sigma to order equal to k, then we can only prove L of s doesn't vanish on the one line. So that's Poisson's method, so it's based on such a positivity argument. So this method works for all automorphic L functions. So in that case, for all the automorphic L functions, we have a zero-free region, y minus c times log the analytic conductor of the L function. And this method, so we can always find such a d of s satisfying those three conditions. So what about Rankin-Selberg L functions? So for Rankin-Selberg L functions, if pi or pi prime is self-dual, then this method still works. And we have a zero-free region for such Rankin-Selberg L functions. So we can always find a Dirichlet series d of s with those three conditions. But as we know, self-dual Cuspidal repetitions are very rare. The density is 0. But in general, if both of them, pi and pi prime, are non-self-dual, this method doesn't work. And in general, we only have a polynomial type, zero free region, due to Bernoulli. So the zero free region is like sigma bigger than y minus a constant divided by the analytic conductor to a power. So that's the best result before our talk. So that's, but in general, that's still the best result. A zero free region, like a sigma, is bigger than y minus a constant log analytic conductor to some power is called a standard zero free region. So we look for such a standard zero free region. So the L function we are interested in our talk is the following. So if f is a cusp form on GLN, and L function has Euler product. So that's, and so it's a degree n L function. And then we define the Rankin-Selberg L function by such an Euler product. So it's L of S f cross f. It's not f cross f tilde. So for this Rankin-Selberg L function, we have function equation s goes to y minus s and analytic continuation. So if f is not self-dual, we know this L function, the Rankin-Selberg, is holomorphic. So here's our new result with Goldfeld. So the first theorem, it says if pi is irreducible Cuspidal, and so pi is tempered at finite places. Then we have a standard zero free region. So sigma is bigger than y minus a constant over log t to the 5. And here, the constant depends on pi and pi depends on pi. So this theorem follows directly from the following lower bound of the Rankin-Selberg L function on the one line. So so the lower bound is L function has a lower bound 1 over log t to the cubic. So theorem 1 follows from theorem 2 by mean value theorem because the derivative of the Rankin-Selberg is bounded by log t to the square. So that's why we have log t to the 5. So from theorem 2 to theorem 1, that's standard from analytic number theory. And notice here f is very general. It's so it's for any Heck-Maass form. So it could be non-self-dual or self-dual. It doesn't matter. And we assumed f is tempered. Another feature is this result is for GLN. And the power is, the zero free region is c over log t to the 5. It's always 5. It doesn't grow with n growing. So it doesn't, it's very, so that's a very important feature. As we said, the classical method doesn't work for such Rankin-Selberg L functions. So the problem is it seems to be very hard to construct that d of s with positive coefficients. So our proof is based on the Einstein series method. In 1976, so Xiaoqing and Sarnak, they introduced the Einstein series method for GLN, and they proved the L function for pi doesn't vanish on the one line. So they didn't use the classical Poisson's method. This is just a non-vanishing, but it's completely, it doesn't give a zero free region, but it's a completely new method. And then later, Xiaoqing proved non-vanishing of Rankin-Selberg L-functions for GLN on the one line using such a method, Einstein series method. Sarnak, in the early 2000s, he made this approach effective. He actually got a standard zero free region for the Riemann zeta function using such a Einstein series method. And then later, with Gilbert and Lapide, they made this approach work for very general L functions. Especially, it includes all the Xiaoqing L functions, all the L functions appearing in the constant term of Einstein series. So it's very powerful, especially they proved the symmetric ninth of the L function on GL2 has such a lower bound, 1 over t to some power, although the analytic property of the symmetric ninth is not completely clear. So there's no way to use the classical method in this case because we really don't know much about the analytic property of the symmetric ninth. So our approach is based on Sarnak's method. So let's recall Sarnak's method on GL2. Let gamma be the modular group, and gamma infinity is the parabolic subgroup. And then we define the Einstein series. So now we consider this integral. And this integral, the x is from 0 to 1, the y is from eta to infinity. So the y, eta is very small. Remember, t goes to infinity, times the L2 norm square of the truncated Einstein series. So here, the truncated Einstein series was used by Selberg in his proof of the Selberg trace formula. And so this truncated, the Einstein series is not in the L2 space, but the truncated Einstein series is. And the truncated Einstein series is, the Einstein series subtracts the tail. And the tail is 0 if y is small than the truncation parameter a. And the tail is the constant term of the Einstein series, y to the s plus phi of s, y to the 1 minus s. Here, phi of s is the ratio of the completed zeta function. So if the y is very big, then we just cut off the constant term in the free expansion of the Einstein series. And then we average over the group. So now the tail is automorphic after we do the averaging. In the original definition of the truncated Einstein series, Selberg didn't make it automorphic. And so he never does the average over the group. So it's Arthur, he made it automorphic. So Sarnak's idea is to consider this integral, and he has an upper bound, 1 over eta, the zeta, so now it's only 1 zeta appears. So in the original definition of I, he multiplies zeta to the square. So now 1 zeta appears in the upper bound, and so log t squared. A is a power of t. And he has a lower bound, 1 over eta, 1 over log t. So comparing the lower bound and the upper bound, we have the theorem. The lower bound of zeta is 1 over log t to the cubic. So although this lower bound is not as good as Vinogradov's best bound, of the zero-free region, but it's a completely new method. So let's recall Sarnak's method, proven lemma 1, the upper bound. So the upper bound, he used the Maass-Selberg relation. The Maass-Selberg relation gives us the L2 norm of the truncated Einstein series. So it's log A minus the logarithmic derivative of phi. So phi is, remember, phi is the ratio of the completed zeta function, and plus the other term. The other term are small because the denominator on the t. So the main term will come from the logarithmic derivative of phi. And yeah, actually this phenomena is not special on GON. The main term comes from the logarithmic derivative of phi if for the truncated Einstein series is from a Cuspidal Einstein series. It's a general phenomenon. So that's the proof of upper bound and the lower bound. The lower bound is very tricky. So first of all, he used the free expansion of the Einstein series. So the free expansion of the Einstein series has a constant term and a non-degenerate term. Non-degenerate term is n when n is not 0. So the non-degenerate term involves the 1 over the completed zeta function, the weighted divisor function times the Bessel function. So after Parseval, so we need to bound the average over the weighted divisor function. So to get a sharp lower bound for the average over the weighted divisor function, so he used the same result. So bounding the number of primes in short intervals. So, so for positive proportional primes p in an interval of size n, so we have such a lower bound. That's from sieve theory. So use that, so he has that lower bound. So the lower bound is trickier. So this approach of Einstein series method works. The main reason is because the zeta appears in the constant term of the Einstein series. That's one of the main reasons to use this method. So now we want to generalize to GLN. So we set up the problem. So now the G is GL2N, and the gamma is SL2N, K is the orthogonal group. So P of NN is the maximal parabolic subgroup. So it has 2 blocks. And N sub P is a unipotent radical, and M sub P is a standard Levy subgroup. So every Z has a Iwasawa decomposition. It's the X matrix times the Y matrix. The X matrix Xij's are real, the Yi's are positive. So on GL2, it's just XZ equals X plus IY. So it's, but that's in general on GLN. So now we define the Cuspidal Einstein series. Using our that Iwasawa decomposition, we can, so in the Levy is M equals M1, M2. So we use the determinant M1 divided by the determinant M2 to raise it to S power times F of M1, F of M2, and then we average over the group. So this Cuspidal Einstein series, F is a Heck mass form for GLN. So this Cuspidal Einstein series lies on GL2N. It was studied by Lalonde, and it has meromorphic continuation to the whole complex plane, and has a functional equation, S goes to Y minus S. And all the poles lie in the constant term of this Einstein series. So this Cuspidal, so the constant term of this Cuspidal Einstein series will involve our Rankin-Selberg L-function. So that's why the method will work. So now let's define cis of S. So that's the ratio of the completed Rankin-Selberg L-function. And the cis of P is the constant term of this Cuspidal Einstein series. So it's a sum. This was due to line length. So this Cuspidal Einstein series has a constant term, cis of P, along the parabolic piece of N. And along other parabolics, the constant terms are 0. So it's a general theory of line length. The constant term disappears along higher rank parabolics. That's due to line length. And then we define the Arthur's definition of the truncated Einstein series. Arthur's definition of the truncated Einstein series is our Cuspidal Einstein series subtracts the tail, and Arthur made it automorphic. So the constant term, we average the constant term over the group gamma. Gamma is on SL2 then. And when the height function, so the height function is defined by the determinant of M1 divided by determinant of M2. So if the height function is bigger than or equal to capital N, capital A is the truncation parameter, then we throw away the tail. Otherwise, you don't do anything. So that's his definition of the truncated Einstein series.
Are you assuming everything is on ramified?
Yeah, unramified. Yeah, simplest case. Haven't considered other case yet. So that's his definition. But due to this sharp truncation, it's very hard to get the free expansion of this truncated Einstein series. So we used a trick. So we'll introduce a modified truncated Einstein series. So we'll introduce a smallest version, a modified truncated Einstein series. So it's defined by this Einstein series. It's a combinatorial identity. So it looks very complicated. The idea is this modified truncated Einstein series, we want to make it for two purposes. So one purpose is it's easier to derive its free expansion. The second purpose is we want to make it in L2 on the line. We want to integrate. Otherwise, we can't just smooth it arbitrarily. Of course, there are many ways to smooth out the truncation. But the problem is, if we smooth it, how do we relate it to our original Einstein series? The first question. And the second question is, we have to make sure it's still in the L2 space, so it doesn't grow. On the line, we want to integrate. So what's the connection of our modified truncated Einstein series and Arthur's truncated Einstein series? So here's a proposition. If our truncation parameter A is like t to the n to the some big power, and yi is less than t to that power n times 2n minus 1, our modified truncated Einstein series is related to Arthur's truncated Einstein series by this identity. Why this is true is just because of the lemma. The height function gets smaller when we act with action of gamma. So that's why if the truncation parameter is very big, then all the tails in the definition of the modified Einstein series, truncated Einstein series, will be gone. So it's essentially just the top three terms. In the definition of the modified truncated Einstein series. So that's because of the lemma. And we used some combinatorics it looks complicated. That's because we want to, it's like we have to make sure it's still in the L2 space. So we have to subtract several terms to make sure the growth terms are canceled and it's still in L2. How we made this construction is because we look at the free expansion of the Einstein series, and we look at the degenerate terms, the growth terms, and then we want to make sure all the terms are canceled. So that's how we constructed this modified truncated Einstein series. Okay, so another lemma. So this lemma tells us our modified truncated Einstein series is related to the Einstein series by this identity. This is true for all the z and all the s. It's just an identity. And this lemma is because of this analytic trick. It's this smoothened trick. So if we smooth out the truncation, and we as a cost, we have that 1 minus 1 over x, that weight. So now, because of this lemma, if we know the free expansion of the Einstein series, then by using this lemma, we just plug in the free expansion of the Einstein series, we can get the free expansion of the modified truncated Einstein series. Okay, so now we have the free expansion of the Cuspidal Einstein series. So the first term is the degenerate term, average over the lower rank group, SL2n minus 1, and plus the non-degenerate term. The non-degenerate term is just the Einstein series integrate with a non-degenerate character, so against a generic character. The first term is the degenerate term, so it comes from the Einstein series integrated against a degenerate character. So the free expansion of this Cuspidal Einstein series is very simple. It's just one degenerate term plus the non-degenerate term. And the proof of this proposition follows from Lalonde's constant term formula. If we know the Lalonde's constant term formula, then we use induction to get the free expansion of the Cuspidal Einstein series. So now, plugging the free expansion of the Einstein series, we have the free expansion of the modified truncated Einstein series. There are many degenerate terms, There are many degenerate terms, and the last term is the non-degenerate term. The degenerate terms are very similar. So now, what's the analog of the big integral I? Of like Sarnak's I, the integral. So on GLN, here's the integral I, analog of I. So it's the L function, the Rankin-Selberg L-function square, absolute value square, and then we integrate on that space, modulo that maximal parabolic subgroup, piece of 2n minus 1, 1. It's a maximal parabolic subgroup. And we introduce some smoothen G and psi. That's just the analytic trick. And because the delta will be very small, so when we do the free expansion, the lower bound will come from the non-degenerate terms when the yi's are very small, like the GL2 case. So anyway, this integral, why we integrate over such a strange domain? The reason is because when we do the unfolding, it gives us a standard Rankin-Selberg structure. Its unfolding gives, so the Mellon transform of psi and the inner integral is just a standard Rankin-Selberg integral. So the absolute value square of that integral of the modified truncated Einstein series, and times the maximal parabolic Einstein series. The maximal parabolic Einstein series, there are no mass forms involved. It's just an average that determine over that quotient space. And so if phi is a mass form, and then the absolute value phi squared times the maximal parabolic Einstein series integrate over this fundamental domain of SL2n. This is just roughly is just the Rankin-Selberg L-function of phi times phi. So that's one reason we integrate over such a domain, because after unfolding, it's just a standard Rankin-Selberg structure. So that's the analog of Sarnak's case. Okay, so now we have to get the upper bound of this integral I. We need some bounds for the maximal parabolic subgroup Einstein series. This maximal parabolic Einstein series is it's much easier to study than the Cuspidal Einstein series, because essentially this maximal parabolic Einstein series is the Epstein Einstein series, and it has an integral representation. So the theta function is defined over that lattice. So because of this integral representation, it has functional equations and analytic continuation and so on. So this Einstein series is much easier. So to get to the bounds of this maximal parabolic Einstein series, so we just using this integral representation and the Poisson summation formula. Because our omega, essentially, because of our smoothing, omega will be very small. So the yi's could be very big. So this bound is really sharp for the yi's. And so essentially, we don't lose anything. This bound is sharp in terms of the yi's. So that's the maximal parabolic Einstein series. And also, like what Sarnak did, we need the Maass-Selberg relation for the Cuspidal Einstein series. So this was Lennon's state for GON. And so the inner product of the Cuspidal Einstein series, Cs of S, are the ratios of the completed Rankin-Selberg L-function. And look, the logarithmic derivative of the Rankin-Selberg L-function is here. So that will be the main term, logarithmic derivative. So that's the Maass-Selberg relation on GON. So here, we get the upper bound for the big integral I. So we shift the line to the 1/2 line, and then we pick up a pole of the maximal parabolic Einstein series at 1. So the first term comes from the pole at 1. And then the next term is the integral over the 1/2 line. And then for the top term, we use Maass-Selberg relation, and also here for the maximal Einstein series, we use our previous bounds, and as well as the Maass-Selberg relation. So that's the upper bound. The lower bound of this integral is trickier because, here's the lower bound, and it's our lower bound. So for the upper bound, we actually don't need to assume F equals G for the Rankin-Selberg. And this method works in general for any Rankin-Selberg L functions, actually on GON times GOM, and we don't need temporariness, or we don't need any assumptions for the upper bound. The setup is very general. But for the lower bound, it's trickier. So for the lower bound, because there are many degenerate terms in the truncated Einstein series, when we use a free expansion, there will be many terms. So it's not obvious what's the analog of Passover in that case. So here, this proposition, the orthogonality of the degenerate terms and non-degenerate terms, this is crucial because when we square the truncated Einstein series, we get degenerate terms times non-degenerate terms. These cross terms will be gone. And we will get the degenerate terms square plus non-degenerate terms square because of this proposition. All the cross terms are gone. So this proposition is not obvious because the degenerate terms are infinite sums, and it's averaging over lower rank group. So the proof of this proposition used induction. On GL2, it's obvious because it's just the constant term is orthogonal to the non-degenerate term. Because the cross terms are gone and we have this lower bound, so we just pick up by positivity, we just pick up the non-degenerate terms. So here, as our original integral I is defined over a complicated domain, the P, this maximal parabolic subgroup, slash that eta to the k. So, but after unfolding, that's another reason using such a domain. So after unfolding, this domain becomes very simple. The UK is just the unipotent subgroup. So it's just a Euclidean integral. The x are from 0 to 1, 0 to 1, and the y is from 0 to infinity. So it becomes a very simple domain. The group integral is gone. So it's just a Euclidean integral because of this unfolding process. So we just, so because of the orthogonality of the degenerate term and the non-degenerate term, we pick up the non-degenerate term. And it turns out this is a main contribution of the lower bound. So because the delta is very small, the yi's essentially are very small. So the main contribution comes from the non-degenerate terms. So if the yi's are big, certainly the constant term will contribute. But here, the yi's are very small. So the non-degenerate terms are the main contribution. So now we need to study the non-degenerate term of this truncated Einstein series. So then we have to introduce the Jaquet-Whittaker function. So Jaquet-Whittaker function is defined by the integral of this I function, the power function, and we integrate over the Euclidean space. And so that's the, so against an additive character. So this was studied by Jaquet. And so on GL2, this is just the K-Bessel function. On GLN, that's the generalization. Because of the 0, 0, 1 integral picks up the diagonal term of the non-degenerate terms, so we only need the Mellon transform of the absolute value square of the Whittaker function. So we don't need the asymptotic formula for the Jaquet-Whittaker function. So we are very lucky. And so the Mellon transform of the Whittaker function on GLN times GLN is just given by these gamma factors. So for gamma functions, we know everything. But for Whittaker function, it's a very hard problem to study asymptotic properties. So now the free coefficients of the Einstein series, the P's coefficient is given by lambda p times the divisor function of p times the Whittaker function and times 1 over the Rankin-Selberg L-function. This was due to Shahidi, the 1 over Rankin-Selberg. And so here we assumed f equals f in our Rankin-Selberg, because only in this case we can separate lambda and the divisor function. For other Rankin-Selberg L functions, L of S, f times g, f is not equal to g, we can't separate lambda and the divisor function. The formula will be like lambda times p to the nit plus lambda prime of p n to the minus 2it. So the Hecke eigenvalues and the divisor functions are mixed, and we don't have a method to do it. But for this special case, only here we assumed f equals g. So the Fourier coefficients are given by such a simple formula, lambda of p times the divisor function. So now we need a sharp lower bound for the mean square for the Hecke eigenvalue at p and the divisor function at p. Well, for the Hecke eigenvalue, so for positive density primes, we have a lower bound, assuming f is tempered. So only here for this lemma, we assumed f is tempered. It's because, so the proof is because it's a result of Jinya Liu and Wang Yanbo. On the average, the lambda square at primes is asymptotically to capital N, or probably times some constant. So that tells us on the average, the lambda of p's are not small. But we want to get a positive proportional primes such that lambda of p is not small. So if at one prime the lambda of p is very big, then that destroys everything. So that's why we have to assume each lambda of p is not very big. So on the average, they are not small, so most of them are not small. So that's why we need a temperedness. Again, like Sarnak did, we have to use same method, same result for the weighted divisor function. So that's because the weighted divisor function has this lower bound, and so when the 2nt log p, so when p is in a short interval, then those primes are bad, because in that case, the weighted divisor function is small. So then we use same method to bound the number of primes in short intervals. So all those bad primes contribute to a density 0 set. So we a very small density set, so we get this positive proportional primes. The weighted divisor function has a lower bound, 1. And we want the product is not small. So because of the previous two lemmas, so these two sets, when lambda of p is not small and the weighted divisor function is small, these two sets has an overlap. So on this overlap, the product is not small. So now, so that's the proof of the lower bound. So everything is sharp up to some logarithm. Okay. So comparing to the lower bound and upper bound, we got that 1 over log t to the cubic, like Sarnak has on GLN. Okay, on the last section, talk about Selberg's conjectures, and Selberg 1950 also introduced Selberg's class. F of S is a Dirichlet series, and it satisfies these conditions. It has a pole at 1 at most, and S minus 1 to the m times F is entire, and it has functional equation, and it satisfies the Riemann-Urian conjecture. So S of n is bounded by n to the epsilon at a scalar product.